And now that we have seen how we will be able to calculate the Q and the V functions for let's say an environment, either deterministic or stochastic, what we want to do is to start discussing about two other functions which are kind of essentials in order for us to solve the MDP problem. And by solving the MDP problem, evidently we mean to find the optimal policy. That's basically what we are trying to do. So there are two equations and two other functions that allow us to actually provide that kind of solution. Of course, they are based on the well-known by now VAQ functions, and they are called the so-called Bellman optimality conditions or functions. And the first one is simply says the following, something kind of initially it looks a bit confusing, but it is kind of fairly intuitive. If you have a range of policies that you have evaluated, and these policies, each policy would give us, if you like, a V pi of S, then you can actually take the maximum for across all of those value functions. Each one of them, as we said, corresponds to a policy to determine what we call the optimal value function, and this applies to both the V functions and the Q functions. So we'll be calling these optimal V functions V stars, and the corresponding Q stars, Q functions Q stars, and we will be using them in order for us to be able to reach, if you like, that kind of desired outcome, which is really the optimal kind of policy. So the way to actually understand this is probably using an example, and then we will see how the recursive formulas kind of look like. So we have actually over here a very simple example, which I think is quite instructive. And this is actually called this kind of a cleaning robot. And the cleaning robot environment is as follows. So there are effectively 6 states. The state 0 is a battery recharge state, and the state 5 is the course of acquisition of garbage. And so the robot is picking up that kind of garbage, and then that is basically the state that transition from state 4 to state 5 results in a reward of 5, while the transition from 1 to 0 results with a reward of 1, and all of other rewards are 0. So the environment is could be a deterministic environment or could be a stochastic environment. Let's take a look at the stochastic environment because in that environment we have, if you like, the determination of the V star and the Q star. More specifically, in this specific example, we are working with the Q star. And in the deterministic environment, we have a probability of 0.8 to reach the desired state. Let's say go left or right. These are the two actions we have, either left or right. And but there is also a probability of other probabilities, non-zero probabilities, to not achieve the goal, and in this case, not transition to the desired state, stay put with probability 0.15 and move in the opposite, in fact, direction with probability 5%. Okay, so this is what makes the environment stochastic, as we discussed, and what we actually can do for each of the actions for all states. We will be, let's say there are two possible intended actions to go left or right. So for each of the possible actions, we will be able to get the Q functions, a Q of S comma A, as we have just said. And so we are going ahead and using the well-known by now Bellman expectation backups and the associated kind of iterative way of solving for the Q function. We have plotted over here the blue and the dashed red lines. Okay, the blue and the dashed red lines. So what Q star is actually going to give us, the Q star is going to be the maximum across these just two polys that we have here for all states. So it will actually be, the Q star will be the blue level over here, the red level over there, and so on, up all the way until state 4. And of course, we are going to have the same value for 0 and 5, but 0 and 5 states are kind of terminating states. This is actually coming out of a textbook that I have included in the references that introduces, if you like, this example. We understand now another example where we have just working with the V star, calculating, if you like, the V star. We have here the so-called recycling robot example from Sutton's textbook. So this robot is just basically collects soda cans, and it has effectively two states that represent, if you like, battery level, so the high and low. And at each state, the agent has to make certain decisions, either to continue to search for the cans, to remain stationary and wait for someone to bring it a can, to head back to the charger and recharge the battery, and so effectively we have action sets which are determined based on what makes sense for the robot to do. So for example, not necessarily to recharge the battery when the state of the battery is high, and definitely we need to do that when it's low. So we define, if you like, two different sets of actions that each one corresponds to the state of the robot. So the rewards are 0 most of the time, but they are becoming positive when the robot secures an empty can, and or large and negative if we just basically exhaust the battery without really being able to reach the charger. Okay, so evidently this is a kind of a more complicated kind of example where we have here some other kind of parameters. So the robot is searching around, and this obviously this results into kind of battery being gradually depleted. We are providing some kind of probability for that, for the battery to go into depletion kind of state and therefore change the state. So if the energy is high, then a period of okay, so that's basically if it is in the high state, then it will be a depletion probability. So the depletion probability is 1 minus alpha over here, and maintains, if you like, the high state with a probability of alpha. So when the period of searching undertaken with an energy level is low, then remains low with beta and depletes the battery with probability of 1 minus beta. Okay, so in that latter stage, the robot must be rescued and the battery is then recharged back to high. So all of these are represented by a finite state machine. So a finite state machine is a very well used, very popular way of determining, if you like, rules and actions based on states and things like that. So in practical systems, so this is a finite state machine for that recycling robot with the corresponding, if you like, actions that are the solid circles over here, and the corresponding probabilities and rewards. The probabilities are evidently associated with the probability of transitioning from a state given an action to another state. Okay, so effectively this S, A, S prime are the triplets that we have seen, and for each S, A, S prime triplet we have a corresponding reward. Evidently the environment is stochastic, so therefore the reward function must be a triplet as compared to deterministic environments where the reward function is just two terms, S and A, since in the deterministic environment the S primes are the expected ones, and we don't have any stochasticity in the environment, so we don't have to specify them. Okay, so that's basically it. Those are the table over here kind of captures the complete environment. And what we will do now is we'll calculate the so-called V star as an expression from effectively repeating exactly what we have seen earlier with the expectation backup, but now this backup is actually going to be called optimality backup. To solve this kind of example, we just want to write the V star of S as an expression, and this expression will actually be we're definitely going to have a max operator for all actions that belong, if you like, to the set of actions for that kind of state. And over here we have said that is going to be Q pi star of S comma A. I mean, this makes sense. And this, of course, is identical to maximum of V pi of S across policies pi. Okay, so, but actually we're writing this way because it is, we are able to sort of, get the sort of the expression in kind of an easier way to understand it. So if we replace the expression for the Q function, the expression for the Q function was, again, this is we have max A. I'm going to skip this A of S for simplicity. Here we had an expectation over pi star. And again, the pi over pi star, this expression, I hope it is understood that behind this kind of, the pi star over here is in fact a conditional. So it is an expectation over the sort of S prime states that we are, the future states that we are able to hit by taking optimal actions. So we have here the return, the expected returns, in other words, given that we are at t at state S and we are taking an action A. And so we can actually continue here. Is an expectation. So what is really that expectation can actually now be written. The derivation is not going to necessarily be given here. V star of st plus 1 given st is equal to s, at is equal to a. And finally, it is max over a of replacing the expectation with summation over S prime and rewards R of the MDP dynamics R plus gamma V star of S prime, which of course says the following: the value of a state under an optimal policy must be equal to the expected return must be equal to the expected return for the best action from that state. And this is basically what the V star kind of represents. And in addition to that, I think it's worthwhile drawing also the backup diagram. So from that kind of state S, we have a set of actions. If we take the maximum operator over, so each of these actions is associated with a state action pair. So if we take the maximum out of these actions, so a state action value functions, which is actually Q. So if we take the maximum out of these kind of Q functions, then effectively we are defining, so over here we have Q pi star of S comma A, and then we have over here we have V star of S. So if we knew the optimal Q function for each of these kind of states, we are able to determine with the max operator the optimal V function for this state S. Okay, so the other thing I think is worthwhile kind of mentioning is what we have mentioned earlier. I want to put this in writing. The thing is that okay, so for each state, S, we go through all policies. This was the cleaning robot example. We go through all policies pi and pick up the policy that maximizes V pi of S. The maximization is done independently for each state. And we may end up with different policies that maximize policies pi that maximize V pi of S for different states. And this is basically what we have seen in this kind of a cleaning robot example, where the policy left was optimal on, let's say, state 1, and the policy right was actually optimal in state 2. If we kind of do the exercise of showing exactly how the V-star calculation will happen for the recycling kind of robot, we have, just to repeat, the V-star of S is max over A of a summation from S prime across S prime and rewards of the MDP dynamics S prime R given S comma A of R plus gamma V star of S prime. Okay, and so for the recycling kind of robot, what we need to do is to calculate, in other words, V star for the H, where H is the so-called high state, high battery state, and this is effectively max. We have a number of actions that we are going to have in the sort of high state. And if you recall the problem statement, the set of actions in the high state is just search and wait, while in the kind of a low state we had actually three possible actions. So we will be symbolizing search with S, wait with W. We need to also produce the V star of the low state, so it will be sort of recharge with R. With RE, because we don't want to use R, because R is also the symbol for our instantaneous reward. So so now that we have here, we're expecting to see a summation of all future states S prime and associated rewards, and the lookup table that we had defined earlier in that problem statement had, if you go back to that kind of a site, then you can actually see the lookup table. The lookup table was giving us from S via an action to S prime. So it is really this lookup table that we have to start plugging into this kind of equations. Okay, so it is max of what now? The first is across two actions. So I'm expecting to see a list over here. So first it is the probability of S prime being high, given that we are in high and we are searching. Of the reward. The reward is going to be R. It's a triplet. The reward function is a triplet. High, searching, high, plus gamma V star of high, plus probability of low given high comma searching, R low searching, sorry, high low searching. In fact, searching low, the action is in the middle. Plus gamma V star of low. So we have future states of S prime to be either remaining in the high or transitioning to low. Okay, and so that's basically what we have here, comma, and we have the second action. So the second action is in the high state is to either search or wait. So the second action is wait. So we have exactly the same thing. High WH plus gamma V star of H plus probability of low now, the second state S prime, given high weight R of high weight low plus gamma V star of low. So that will actually be the expression for the V star high. And then we can actually plug in the corresponding transition probabilities here with that were given, that involves alpha and betas, and come up with an associated reward functions values that are given in the table, and come up with an expression that will involve only the V star. So I'm going to give you that expression by using, if you like, the site. So in the site you can actually see the steps that we have taken as well. So this is the final expression that involves the rewards for searching, the rewards for weight, which are all numbers. The only unknown here is the V star of high. So we have V star of high over there and V star of high on the right-hand side. And also we have V star of low on the right-hand side. Okay, so that's the first equation. Evidently, it's a nonlinear equation. That's a first nonlinear equation. And we can actually go ahead and repeat the same exercise for the second nonlinear equation, V star of low. So we have two nonlinear equations with two unknowns, and the process that we will specify right now, called policy iteration, is able to help us so come up with a solution for this nonlinear problem.